Okay, it's lecture number 6. The last two lectures we talked about the geometric formulation of special relativity, which the message is that the best way to bring about the symmetry between space and time is to unite them in a four-dimensional space-time manifold. Okay. So tensor equation in four-dimensional space-time, if you're writing tensors, then the symmetry under Lorentz transformation is automatic. Okay. And the four tensors, so therefore we need to work out the tensor for physics. Tensor rank 1 and 2. We have like a for velocity, for momentum, and rank 2 electromagnetic field and energy momentum tensor. The only topic left in chapter 3 is the space-time diagram, which we're going to discuss today. And also we're going to start on chapter 4, looking for a relativity theory of gravitation. Now, a space-time diagram, basically, we have a time axis and the space, but we can't represent the three-dimensional space. Here, I just take a one-dimension x. In this case, this space diagram is just a plane. And a point in the space we call word point is an event because it has time and space coordinates. And when it moves, you trace out a line which we call word line, which is the history of events. Okay, and if this particle is light, it will trace out a 45 degree because light travel at ct is just x over t. Ct is equal 1. So just the word line for light signal. And we can talk about so-called space-like region here and time-like region there. The important part, the role of the space-time diagram is really helps us to understand the causal structure of space and time. Let's contrast that to before relativity, before Einstein relativity. We have a space-time diagram. In fact, here I draw two dimensions, x, y, space, and there's the time axis. And we can divide the regions into all the parts can reach. This is called future, which is just in this case positive t, and the region from which particle can arrive from, and that's the past, which in this case all the region was negative t. All I'm talking with respect to the point right here in the center P. Now, if it's neither future nor past, this plane is simultaneous. Okay, so the point in the pre-relative space-time, we can discuss space at any given time. Okay, and so in other words, we can study space and time separately. In relative physics, we will find that the causal disconnected region, in which you cannot be has cause-effect connection, is much larger than just a three-dimensional space. In fact, it's a four-dimensional subspace of space-time. Remember that we have the invariant interval in which in any coordinates this s value does not change. So therefore, we can use s value to characterize the region in space and time because it does not depends on coordinates. Again, we are talking with respect to the origin. Okay, remember we say x, y, and that they are talking about intervals from to the origin. Okay, so here's a relativistic space-time diagram, and we can separate into different regions. In particular, for example, s equal to 0 is we call light-like or null-like and region, which means the events along here are connected by light signals. But for light signal, of course, the displacement is equal to the ct square. So and so you can see also it's a 45 line now traced out into a cone. So these are called light cones. Okay. Now for the green region, it's called space-like region. here the s squared is greater than uh, 0, which means that the distance traveled from origin, x squared plus yc squared, is greater than c. So it was the connection to the origin in, involves, if you want, a speed greater than speed of light, which is not possible. And so anyway, this is so that the causal disconnected from the origin, not just the like here a plane, but it's really much larger region. And then of course within the light cone, which is s squared less than 0, and which is it was any any point connected to origin with a speed less than speed of light. So that's possible. So it's this these are called light-like, past light-like, future light-like. Now, of course, here I drew the space-time diagram talking about a different region, all respect to origin. The light with respect to origin. It doesn't have to be. In fact, any point space-time you can consider is a light cone. Okay. And the point is that any whirl line, which means possible trajectory, must be contained within the light cone, just like here. Okay, it has to be time-like. Okay. So when a particle moves, like at P1, it can only the next step must be within the light cone. To go to P2, the next step must be within its own light cone. P3 must be within the light cone. So therefore, any particle can only proceed in a direction ever increasing time, okay, into the future. You can't stop your biological clock. Just, okay, there's no way to to go backwards. So now we're talking about how the space-time diagram represents the Lorentz transformation. Here's the Lorentz transformation. Okay. So the when you from x and t go to x prime t prime, the x prime axis, of course, correspond to a fixed t prime region. So therefore, t prime equal to 0, it has these conditions. Okay, and so this condition of ct equal to beta x, it means also t over x equal to beta. So it was a constant slope. So therefore, the new x prime axis again is a straight line, and making it with the slope of beta in the unprimed xt plot. Okay, so therefore it involves a counterclock rotation of the x to x prime. It was counter this slope beta, and the time axis can work out the same way. If the t prime axis, of course, corresponds to x prime equals 0, and you can work the same way. This has slope of 1 over beta. Okay, so this is a clockwise rotation. This is counterclock. Now that's also for beta to be positive. Beta can be negative, of course. And then, of course, the axis, instead of close in, the t prime will be here and x prime will be here. So the two axes will be, instead of close in, will be open up. And the important thing you notice, the angle here, okay, the two angles are about theta. This equal angle, the opposite but equal angle. The reason it has to be equal angle because whatever you do with the coordinate changes, the light signal always have slope 1. So therefore, originally 45 degrees, now this is still must be bisect equally between t prime and the x prime axis. So therefore, because this line is still have slope 1, so therefore you must have equal angle on both sides. So it's easy to understand why these two axes must be closing or open up the same amount. Okay, you've seen the space diagram. I'm going to ask you to do some simple exercise. I will ask you to draw a sequence of whirl points. First, you know what whirl point is. Represent the equal interval ticking, in which each tick is an event, and it's represented by a word point. Okay. Now, so in the one coordinates, you have clocks, static clocks sitting same position, and but clicking away at different time. I mean, at different time, but equal time intervals. Okay. Now you can see how this is seen by a moving uh, observer. Okay. And so in which I'm asking you to draw two word lines. One's the word line respect to the coordinate in which the clock is at rest, and another word line with respect to the observer which is moving. The second problem I ask you to do is to use a space diagram to demonstrate the phenomenon of relativity simultaneity. Remember, if two events are simultaneous in one coordinates, may be seen to have different times uh, in another coordinates. So it's very simple. You can just see them in a space-time diagram. Okay, you can pause and I'm not going to stop here.